Welcome to The Explainer. Take a second right now. Just look down at the pattern on the shirt you're wearing. We are surrounded by these designs literally every single day, right? But we rarely stop to think about the microscopic battle it actually takes to create them. So today we're exploring the absolutely incredible art and science of textile printing. We're going to trace a fascinating journey that stretches all the way from ancient 12th century carved wooden blocks right up to modern computer-driven digital pixels. It's just a brilliant blend of ancient craftsmanship and cutting-edge chemistry. Okay, let's dive into this. Here is our micro to macro, recipe to reality roadmap for this explainer. First, theory of localized dyeing. Second, anatomy of the paste. Third, fixation and post-treatment. Fourth, 4 methods of print mechanics. And finally, number 5, the master printer's matrix.
Section 1. Theory of localized dyeing. The foundational challenge of printing really comes down to one seemingly simple question. How do you get liquid color to stay in exactly one spot, permanently, without spreading?
You know, to really understand printing, we first kind of have to contrast it with regular dyeing. Think of standard dyeing like painting an entire room with a thick roller. You plunge a piece of fabric into a giant vat of liquid, and the whole textile absorbs that color completely and evenly. Printing, on the other hand, well, that's like using a super fine-tipped pen to draw a detailed portrait. We're trying to place color in highly specific, precisely restricted boundaries. No bleeding allowed. So, as you can see, uniform immersion completely saturates the fabric. But printing is fundamentally localized dyeing. By intentionally restricting the colorant to a predetermined area, we totally transform a blank, uniform surface into a highly precise, complex design. The real trick, though, the million-dollar question, is figuring out exactly how to restrict that colorant so it doesn't just spread everywhere the second it hits the cloth. Which brings us to Section 2, anatomy of the paste. To stop that liquid from spreading, we actually have to treat our print paste exactly like a highly specialized, high-stakes baking recipe. Every successful print paste basically consists of 3 fundamental layers. First up, you've got the colorant, your dye or pigment, which is the aesthetic core of your design. Second, you have the medium. This is usually just a small, very precise amount of water used to dissolve and disperse those dye molecules. But here's the catch. Water alone will just wick right through the fabric fibers like a paper towel soaking up a kitchen spill. So you absolutely need the third and most crucial element, the control. And that, my friends, is the thickener. Now, what's really interesting about this slide is the profound difference that thickener actually makes. Without it, the dye mixture just prematurely splashes and bleeds all over the place, completely ruining any chance of getting a crisp image. But with the exact right physical and chemical viscosity, the thickener holds the dye in this perfect contained little dome. Industry professionals actually achieve this using natural gums like acacia or starches, sometimes modified naturals like sodium alginate, or even fully synthetic thickeners like PVA. Basically, the thickener creates that critical boundary we need. All right, moving on to Section 3, fixation and post-treatment. So our perfectly thickened batter is now sitting nicely on the cloth in the exact shape we want. But if you washed it right now, your beautiful design would just swirl right down the drain. No good! We need to bake it into the fibers and then, effectively, wash the dishes. We do this baking through what's called the fixation phase, which uses steam and heat in 3 sequential steps. First, the paste just rests on the fabric. Second, we apply steam, which causes the textile fibers to literally swell and open up, kind of like a dry sponge soaking up water. And third, as those fibers open wide, the dye molecules actually leave the thickener and penetrate deep inside the fiber structure. Check out how those blue dye molecules actually migrate from the dome of the paste all the way down into the swollen open fiber core once that steam is applied. It's pretty amazing. However, there's a fascinating caveat here, and it's called the thermoplastic exception. See, if you're printing on synthetic, hydrophobic fibers, like polyester, for example, they absolutely hate water and they will not swell in steam. So for these, you have to use intense, dry heat. You're essentially melting the plastic fiber just enough to let the color slip inside and then letting it cool down to trap the dye forever. Once the dye has successfully penetrated, the textile moves to post-treatment, which revolves around an incredibly important wash. See, after steaming, the thickener has done its job, and it actually dries up into this cracked, stiff shell. Think of it kind of like a clay mud mask drying on your face. The wash is this aggressive process, designed to entirely scrub away that thickener shell and any leftover printing auxiliaries that just didn't bind to the fiber.
And this chemical gauntlet has a genuinely beautiful payoff. By washing away all that structural scaffolding of the thickener, you're left with only the permanent locked-in dye molecules. The fabric actually returns to being soft and pliable. And this is exactly why your favorite high-quality graphic tees can survive hundreds of trips through the laundry without the image washing away. The color isn't just sitting on top. It is permanently bound right inside the fiber. Section 4. 4 methods of print mechanics. So we know the microscopic chemistry, but how do we actually deliver this precise paste onto the fabric at a massive industrial scale? Well, we begin with the heritage method, block printing. This originated as a highly skilled manual process way back in 12th century India, in regions like Rajasthan and Gujarat. And this method involves stamping the paste using incredibly intricately carved wooden blocks. Now, it is stunningly beautiful craftwork, for sure, but it comes with a massive mechanical constraint. If you want to change the size of your print by even a tiny fraction of an inch, you literally have to spend weeks painstakingly carving a completely new wooden block. Because of all that sheer manual labor, the industry really had to evolve. But this evolution required adopting an absolute, non-negotiable rule of production for our next method, and that rule is 1 color equals 1 screen. And that brings us to screen printing, which is the modern industry standard. Whether you're using flatbed stencils or, much more commonly, rotary continuous cylinders, this is the undisputed workhorse of the textile industry. Rotary screens allow a squeegee to force paste through a porous mesh stencil continuously as the fabric just rolls by, running in perfect alignment at absolutely staggering industrial speeds. It's the most economical, high-production method available today. But you gotta remember that golden rule. If your design has 12 colors, you need 12 completely separate rotary screens running in tandem. Next up, we have a uniquely fascinating physics trick, sublimation, or transfer printing. This is the process of taking volatile dispersed dyes, and by volatile, I mean dyes that desperately want to turn into a gas, printing them onto a temporary paper carrier, and essentially baking them directly onto the final textile. Here's how it works. In phase 1, you use a standard large format printer to print your design onto a roll of paper. Simple enough. Then, in phase 2, you place that printed paper right against your fabric and run the whole shebang through a high-temperature heat press. The heat causes the dye on the paper to sublimate, meaning it turns into a gas, and it literally leaps over to securely bond with the fabric. Because this is baked entirely through gas, it brilliantly bypasses the need for any messy liquid thickeners altogether. A real game changer. Finally, we have digital printing. Now, this method offers unprecedented flexibility. It uses computer-driven inkjet nozzles to spray specialized dyes or pigments directly onto the fabric. There is zero physical setup here, no blocks to carve, no screens to prep whatsoever. This allows for infinite design variation and incredibly rapid prototyping. However, it's a really interesting industry trade-off. You get that infinite variation up front, but unless you're using very specific pigments, you still rely on entirely separate, massive, industrial-scale steaming and washing machines on the back end to actually fix that color into the fabric. And this brilliantly illustrates our final section, Section 5, the Master Printer's Matrix. Let's synthesize these methods. When you weigh these methods against each other side by side, the evolutionary trade-offs become crystal clear. You're trading the manual slowness and fixed size of carved wood for the blistering speed and economical scale of rotary screens. Though, of course, those screens leave you with that strict 1 screen per color constraint. Meanwhile, transfer and digital printing utilize CMYK color mixing. This offers up to infinite, photorealistic variation operating at medium to high speeds, completely bypassing the physical limitations of carved blocks and cut stencils. But ultimately, whether a master printer is carefully placing an ancient carved wooden block in 12th century India or configuring microscopic computer-guided inkjet nozzles today, their fundamental objective remains completely, beautifully unchanged. They are all seeking localized, beautiful, and permanent color. We've seen how chemical thickeners, steam fixation, and sheer mechanical ingenuity solve the complex problem of bleeding dye, but it really makes you wonder, doesn't it? As technology evolves completely past the need for physical setup, as digital nozzles get faster and chemical bonds get stronger, what new, seemingly impossible patterns will the master printer conquer next? Keep that in mind next time you look at the shirt on your back. Thank you so much for joining me on this explainer, and as always, keep learning.